I don't know if you were ever on the internet, but sometimes I do look at stuff. And there's this case that just finished, Sanderson versus Paltrow, and that's Gwyneth Paltrow. Of course, you know her from Iron Man. Hopefully, you don't know her from Goop because that's just bad. Um, and I don't really care about the case. But so the short of the case is this. So here's some guy and he's on skis, and then here's some woman on skis, and they collide, and he gets hurt, and then so he sues her. That's where we're at. And as part of the suit or whatever, not a lawyer, they they brought in two expert witnesses. And the first one is this Dr. I think it's Bon. I can't remember how to spell it. But so what he did was he said, look, they fell. They crashed. Paltrow fell on top of Sanderson and broke his ribs. It's her fault. Fine. I don't really care about that. What I care about is his next step. Let's use some physics and show that that's correct. So I have his thing. You can find this online. You got to search. And I'm not really great at searching for this kind of stuff, but I found it in a video. This is a snapshot of a video. I'm going to explain it to you. And this is what he did. And I don't think it's great. And it has an error. And then we'll talk about that. So I have my red pen so I can grade this. So he says, hey, let's calculate. And everything I know is from the rebuttal witness talking about this. I found his testimony, but I didn't see this in there. So it may have been not live. So he said, okay, we're going to calculate the speed. So he says, if you take a person like this, it's the same as if they fall over, and which I don't think is true, as their center mass falling to the ground. So how fast would they be going when they are in this position, hitting the ground, falling a distance h? So he says, okay, I'm going to use the kinematic equation. That's what he has right here. I'll rewrite it. He wrote, I can switch to red. He has x equals x naught plus v0t plus 1/2 a t squared. So this is, of course, the kinematic equation. This says if you have an object with a constant acceleration in one dimension, and you start at t equals 0 with v 0 equals whatever, and x0 equals whatever, then you can find the final position. So this is one of the kinematic equations to find that, and that's fine. Now, normally, we don't use the x direction for up and down, but it's not wrong. It's just not normal. Okay, so then he says that the initial velocity is 0, so that's what he crossed that out right there. And he says the initial x is 0. Okay, that's fine. And also he's writing his zeros like that, which I don't like. But, you do you. Okay, I don't do that. That would be the Greek letter phi, but whatever. So he must be having this. That's positive x is the downward direction, such that they start up here at x equals 0 and they fall down. It works fine, because then you have a positive acceleration. Again, why is there a positive acceleration of 9.8? This is actually the gravitational field, and the force also depends on that gravitational field, so you get that acceleration. So solving this for time, if this is only true if the initial and final position, the initial position is 0 and the initial velocity is 0, then they get 2 final position over a, and that should be the whole thing is square rooted. Then this is the height of one of the people. This is the center mass, which I guess would be halfway, a little bit higher. That's the conversion into meters. Plug it into here. Left off a number right there. This seems to be 0.4666 seconds. That seems to be okay. And then he plugs that into here to get the final velocity. Now, so here is another problem. That's a problem. So let's just write this out in a better way. So if I know the time, let's see, that's the other sheet. If I know the time, so let's just treat this as a falling ball. And here's the thing. So if I know the time, and v initial is 0, and I want to find the velocity right before it hits the ground. We'll call that v2. Then I could say the acceleration is the change in velocity with respect to time. And that's going to be v2 minus v0 over delta t. And this is for constant acceleration, which is what we have here. So I can solve for v2. It's going to be v0 plus a delta t. And then if that's 0, that's fine. I would have an a is negative 9.8, and then the t of 0.467. And then I would get the final velocity. Okay, that's fine. But you'll notice right here that he wrote v equals 1/2 at. I really don't know where he got that from. It must be, he must have said, okay, if I divide this, oh, that's what he did. Oh, he said this. He said, I'm going to solve for the velocity. I'm going to make this a velocity. X over t is velocity, which is not. Velocity is a change in position over change in time, but whatever. Then I need to divide this by time, and that cancels without 0 anyway. That cancels with one of that, and I get v equals 1/2 at. You know, that's just amazing that you would be an expert witness and make that mistake. I think that's what they did. Okay, that's fine. The next thing this guy did was he used that velocity to calculate the impact force. So in this case, he has this situation. Here is the person. Let's draw the person as just a ball falling, and then here's the speed right before contact, and then they kind of squish. So this distance that they squish is the distance d. And during that time, there's a force pushing up on the player, the person. So the work would be negative fd, right? Because if it's a constant force, work is the force times displacement, but they're in opposite directions because the distance is down. And that's going to be equal to the change in kinetic energy. So I would say the change in kinetic energy, this is K1, K2. Oh, I'm sorry, they're using this. That's the right way to do it. K1 is right before the collision. K2 is right after. So negative Fd is the final kinetic energy, which is 0, minus initial 1/2 m v1 squared, which he just solved for, wrongly so. The negatives cancel, and F is 1/2 m v1 squared over d. So there's your 1/2. That's the mass of both of the people. There are two people stacked. That's the wrong velocity. And this is, he used a 3-inch compression during impact. I don't know where he got that, but that's what he did. And so he got that value. This is using a different distance of 5 inches. And so you get a lower force. And then I guess this is like the average or something. I don't know where he got this number, but it's in between those two. And he said, let's just use that. And he said, oh, therefore the ribs broke. So, I mean, I think the biggest mistake, I mean, it's not the way I do the problem. I'll show you how I would do the problem at the end. But let's talk about what they did first. So I think the biggest mistake is this. I feel confident this is what he did. He said, if I take x divided by t, that's velocity. So let's divide this by t, which is, I've never seen that mistake before, and I'm kind of excited to see that. But let's move on. So the next person was this Dr. Schur. I have a picture of him from the video. And he was brought in to say, hey, everything that guy said was wrong. That's from my cousin Vinny. And so what he does here, which I do not like, but is not necessarily wrong, he basically says, okay, V equals AT. You can't see that. V equals AT, which I don't like that one either. I would say the acceleration is let me put it right here. The acceleration is the change in velocity with respect to time. So it's v2 minus v1 over delta t. I mean, this is true if the initial velocity is 0 and if your t is your time interval. So it's just not a nice way of writing it. He defines kinetic energy. He does the same work. He uses a different mass. And he shows that that guy had the wrong velocity. It'd actually be a lot faster. And even without being two people stacked on top of each other, it would have a large force. And that was that. But I don't like it. It's just sloppy. It just looks sloppy. So let's solve this problem the best way. And it's even then, it's not the best problem. So imagine that I have a ground. And I'm going to explain this so everyone, even a lawyer, could understand it. Ha, I'm just kidding. How about I explain this so even a physics expert witness can understand it? This ball is going to fall, and then it's going to get smushed. It's going to impact. We actually do this problem in physics class. That's why it's really, really great. And let's say this is y equals 0. And this is my x and y axis. And so these are things that, if you're doing a real problem, you kind of have to define what's your x-axis, what's your y-axis, where is y equal to 0, where is x equal to 0. It doesn't matter in this case. And so I'm going to call this y1, and that's position 1. And let's call this right before it collides y2, and then after it collides y3. So we actually have 3 positions that we don't need all 3, but I'm just trying to be clear here. Now, in a situation like this, there's a couple forces that are interacting with the ball. There's the downward gravitational force. I'll call that Fg. So Fg is mg, where g is the gravitational field, and it's going to be equal to the vector 0, negative 9.8, 0 newtons per kilogram. Sorry. And then during impact, there's going to be this force pushing up, as well as a downward gravitational force. This one's going to be much greater. F floor, I'll call it. It's the ground. It was on a skiing thing, but I already put F. So I can't go back. I can't change that. And we don't know that, and we want to find that. So in this case, if we're trying to find that that force, I gave it away, and we're dealing with this situation, we could use, like they did, find the time it takes to fall so we can find the velocity. But you're doing something that you don't need to do, because who cares about the time? Instead, we can use the work energy principle. This says the work is a change in energy, where we define work as the integral from point 1 to point 2 of F dot dr. Now, if the force is constant, which we'll assume it is, then we can just say F dot delta r, and both of those are vectors, and that is the dot product. Now, in order to do work and in order to use energy, we have to declare our system. So let's say the system consisting of, I only have one person, so I'll say the person plus the earth. If that is my system, then I have this gravitational force pulling down on the person, but that force pulls up on the earth. And so that means that this is an internal force and does not do external work. So there's no work done by gravity. Instead, we'll have a change in gravitational potential energy, mg delta y. We'll also have a change in kinetic energy, 1/2 m, well, let's say kinetic energy is 1/2 mv squared. And so the change would just be final minus initial. So doing this tells me 2 things. It tells me what do I have to concern with for energies and what's the work. And so in this case, the only thing that's going to do work is this force from the floor. So we can calculate the work. It's going to be F floor dot delta r. Let's write delta r as a vector, because this person's going to go from y2 to y3. So I'm going to write that as the vector 0, y3 minus y2, 0. So this change in height, which he uses 3 inches, which is weird to switch back and forth between metric and whatever, but whatever. It doesn't really matter. This is in meters. So if I do that and I have my gravitation, my floor force, is I'm going to assume is only in the y direction. So F is going to be 0, FF, 0. When I take the dot product between these two, it's just going to be work. It's going to be 0 times 0 plus FF times y3 minus y2 times plus 0 times 0. So it's just going to be, yeah. And it looks like it's positive, but it's not. FF y3 minus y2. Because remember, y2 is right here. It's higher than y3. So this is a negative number. So I'm going to get a negative work. That's important. And now I'm going to set that equal to my change in kinetic plus change in gravitational potential energy. So let's write that out. Move this up a little bit. So I'm going to write F y3 minus y2 equals the final kinetic, K2, minus initial kinetic, K. Actually, this is K3, K1. So I'm going from 1 to 3. Plus U3 minus U1. Now, there's some zeros here, right? And that's really nice. This shows you how easy this problem is when you do it the right way. The initial velocity at position 1 is 0. He started from rest. So the initial kinetic energy is 0. The final kinetic energy is 0 because he stopped. Isn't that nice? The final gravitational potential energy is 0. Isn't that nice? And the initial potential energy is mgy1. So if we put this all together, new sheet of paper so I can calculate stuff, I can get the same answer. So I get ff times y3 minus y2 is the negative mg y1. So y1 is going to be equal to the height. They used, what they use? They used 3.5 feet. Where's the value? Oh, here it is. 3.5 feet was 1.06 meters. G is the magnitude of the gravitational field, so that's 9.8 newtons per kilogram. The mass, you could, if you use both people, they use 136 of the kilograms, the two people. Y3 is going to be, well, it doesn't really matter. Y3 minus Y2 is negative 3 inches, which is negative 0.76 meters. And then you can solve this for the force. F force equals negative mg y1 over y3 minus y2. And there you go. And you should get the same value. But I think it does it a much better way. Now, there are some problems with this method right here. Let's see, let's use this picture right here. Both of these, one, you don't need the time. You're finding the time just to find the velocity. We don't even care. No one cares about that. Sorry, old habit. He's already got a beard, so I'm just kind of filling it in. But even then, this is kind of a difficult situation. If I have a person, and that's their center of mass right there, I mean, they're not just falling straight down. I think a much better model would be a tipping over human. Like that. And so then it's a little bit more complicated problem, but if I was preparing this for a deposition and someone was paying me, I would definitely do it both ways and say, well, does that even make a difference? I don't know that they did that. The other important thing is this work equals F dot delta R. We calculated that. That assumes the force is constant, and it's not going to be constant. In fact, suppose you plotted the impact force as a function of time. It's probably going to look like this. And so this is the average, but it could peak a little bit higher, or quite a bit higher, depending on the kind of contact. These calculations of impact forces are very, very difficult. They're very difficult because we often don't know the distance. We don't know the kind of impact force. One of the things I would do, just to model it the best way, is to say, okay, what if they hit a spring and that spring makes them stop? The spring's not going to give a constant force, but you can use that to kind of estimate the maximum force on the person. I mean, that's what I would do if someone paid me to do that. Hint, hint. But overall, I think the first guy, I mean, it was just a classic mistake. The second most classic mistake, the first being getting in a ground war in Asia, getting involved in a ground war in Asia. The second most common mistake is going against the Sicilian when death is on the line. But dividing both sides by t to solve for x, it goes back to this classic mistake, which I hate to see when students put that. That's not true. Don't do that. That's not true. Okay, so that's my analysis of the Sanderson versus Paltrow case. It was kind of fun. I don't really like cases, like I said. I think the only reason that this was even in the news because one of the people was famous, and that was at the end.